So uh, let's start, guys. So our seminar will be about quantization. And quantization, just large language models. So I want to show you a small presentation. Just a second, please. Well, I just want to log in in green face and not show the credentials. So that's all. Yeah. So this is our seminar, our notebook for today. And here is a small presentation about quantization. So, well, first of all, so quantization really need for sometimes for efficient large language model inference, especially in resource constrained environments, like, for example, smartphones, drones, maybe some laptops too. So all neural network typically use 32-bit floating point precision during training, which is computationally expensive and memory intensive. So I think I can show you some article. It's in a, I'm sorry, it's in Russian, but he is have real great formulas, yes, and images. It's great for just like an example. So yes, maybe some of you maybe heard about mixed precision method. So it's when you have floating point formats. Yes, floating points 32. This is our standard single precision. It's really huge, the 32 bits. Yes, so and we can make a half precision. So, for example, we can reduce mantissa or even exponent. Yes, here, and make, for example, bfloat 16 is when we have 8 bits in exponent, and 7 bits for mantissa. Of course, this is the range quite not really smaller, but it's we just reduce the precision. So and so one small example is it's for floating point 16. So it's a half precision. So when you have 5 bits for exponent, and 10 bits for mantissa. So we have some master copy of weights for this. There's some methods which transfer from the floating point 32 to the update master weights, so it's floating point 16, etc. But I think today quantization is a bit different. Not just a mixed precision, not reducing precision. Yes, reducing, and we reduce the memory and improve our resources, improve our computation. So quantization reduces the precision of weights and activations to lower bit widths, for example, 8-bit or even 4-bit integers. Yes, significantly cutting memory usage and computational costs while maintaining accuracy. So this is the key. This is the key of quantization of any quantization quant method. So and so sometimes I want to show you. So really, it's a linear quantization. I think I'll move to this one. So It's when you have so the range from R mean and R max, and you want to create quant mean and quant max. So, and you have 0 point from here, for example. Yes, you have, for example, just from 100 to minus 100 to 100. Yes, so and you have 0. Of course, when you want to reduce this range, yes, to the new range, 0 will change 0 point. So the formula which create from quantization range to the normal range, it's here. So it's when we have to quantized value. Yes, we have to make quantization BS, for example, yes, and original, and make our original value. And we have here the scale. Of course, to make the inverse operation, so we have round range, yes, so it's range to a scale. We have to divide it plus 0 point, and then we round it and make int. So for example, we in such way we can reverse, so we can make from range, a normal range, to the quantized range. Yes, really great question. How we can define scale and the 0 point? So it's pretty simple. We have some, yes, we have to define our range, our points, yes, for example, our mean, our max, yes, or quantization mean, Qmax, yes, and then we can compute extreme values. It's pretty simple, just we have the same formulas, yes. So in this quantized range, we can define something, yes. And scale will be this formula, so we can find it pretty similar to the formula of the line from a linear algebra, but it's like the same. So we divide the differences between max and mean range points from the normal range and quantized range. So, and 0 point will be so some similar. Yes, we can find it from this formula. So, but make quantized mean and R mean. So, and here we divide by the scale, yes, which we compute here. So around and make it into. So this will be 0 point. So if 0 point will be more than quantized max or less than quantized mean, we can divide it like a quantized mean and make so just just so 0 point will be here, so yes, and we will divide, so we'll define our mean, all these values to the quantized mean. So this is will be the BS. So if we want to make this symmetric map, yes, so we can notice so that 0 point in the original range, so it's not the same, it's not the symmetric, it can be not symmetric in a quantized range. Sometimes it's really we really need it. We need to make symmetric quantization, because asymmetric, it's when our mean and the absolute value of our mean don't equal doesn't equal to the absolute value our max. So, and if we have so the same, if we have symmetric quantization, so if you of course, it's obvious. So we have such ranges, yes, here, because it's symmetric. So we can define the same value with the another sign. So, and we can make the 0 point just like the divide our max by quant max. That's all. So, and then we can define the quantization, this formula is from the one range to the quantized range. So, of course, we have some another topics. Yes, it will be this quantization. So this is, I think, the main rules about symmetric signed, symmetric unsigned, as you can see. Yes, it's when we define the minimum, yes, of the quantized range, like it's 0, yes, and asymmetric. So I think it's really simple here. But if you have some questions, so you can ask me now, because I think we will move to the some new points of quantization. So, okay, 3, 2, 1. Okay, we'll move to point granularity. So, quantization can be applied per tensor or entire tensor, for example, or per channel, each output channel. So I will show you. So it's I'm very sorry. So I show you just some Russian articles, some Russian paper. So with some illustrations, with some images, because the source of this page is quantization depth, and it's was the Hugging Face course just in a collaboration with the DeepMind .ai. So, but it's access denied. I don't really know why. So it's really strange for me because I did. So this is my article. So I did some about linear quantization post. Yes, and I really wanted to tell my people in my channel to about quantization, about this course, just a summary of the course, and it was really great. And I wanted here to show some illustrations and some code from it. And I got this one. I don't really know why, quite so. So, but overall, I'm really happy that I saved some information. Of course, overall in Russian, but by the way, so with the great images from these course, and I think it's great. It's great to have something just near hand. So about granularity. So of course. We don't want to compute all 0 points and scales for the all tensor, yes, because it's can so we can lost precision, yes, because it's in negative sense for precision. It's better to compute separate 0 points and scale per group. For example, for each row or even some per group, I mean group of n elements together on one axis. Yes, so here it's per channel. So not per tensor, just per channel, or even in group elements in one channel. So of course, if you compute, so if you reduce yes elements, the number of elements in your group, the more precision, more accurate will be your quantization. But of course you have to just you have to notice that the sense of quantization it's you have to some memory sources for save some values for this quantization. For each group, you have to save 0 point, yes, and scale for each group. So if you have really small number of elements in your group, so you will have to save a lot values. So and I really recommend you to begin with quantization per channel because it's pretty simple and it's I think it's some balance with memory storage. Yes, if you don't, if you see, for example, so this quantized method really don't apply to you for a case, so you have a bad precision. Yeah, you can reduce the elements in a channel, yes, and make the per group quantization and see something and check the memory, of course. So what's more? Well, activation linear quantization. It's about we can quantize the weights, and it's great. It's great. We'll only try today. So this, but we of course we can quantize activation, because activations, it's the same some values in a 14 points precision, yes, 32. So and we can reduce the precision of activation and in a balance with an accuracy. So, and we optimize our computations and our memory resources. So, if we want to quantize the weights and activation, we really need some type of the data of the 8-bit memory. So this is why we use int 8 or int 4. So in this case, because it's supported and it's really comfortable to quantize. So in some because we have to use these type of data because we have to dequantize. We dequantize our resource, our values. So, and this is why we really need int 8 or int 4. So, because we have to support 8-bit memory. Well, so here the example how we can quantize the to 2-bit yes, from the for example from 14.32 to the 2-bit, only 2 bits. So I read an article, so it was in the previous year. So when some Chinese scientists they did quantization method which can quantize to the 1-bit memory format. It's something extreme quantization, of course, but I want to show you how we can quantize such way. Of course, models couldn't work in it format, so it's great to storage model, yes, in these weight specking or extreme quantization. We can store it and for example, in some, I don't know, in some server, yes. And when we really need this model, for example, we trained a large language model, yes, we trained this such, I don't know, just a couple of months, yes, and then we wanted to effectively store it. Of course, these large language model can wait so a lot, so 100 gigabytes or 200 gigabytes, so it's a lot. It's a lot for server, even for a really great, powerful server. So, and we want to quantize it and to store, only store. We don't want to use it. And then just in, I don't know, just in the next year, want to use it, yes, or something else. So this is what we can do. So if we have some 4 tensor in a 4 numbers in a u unsigned int 8, for example, yes, we can quantize to this format, yes, to the int 8. So it's not a problem. We just have this linear quantization, yes. So, and this is the bit. So this is the binary numbers, yeah, the binary format of these numbers in unsigned int 8. So we have just a 1, 0, 3, and a 2. So, and of course, as you can see, so we have a lot of zeros here on the left side. Yes, on each number. Of course, we don't want to use the memory for these zeros, and it's they don't have no information. Yes, so we can cut these zeros, just 6 zeros, 6 bits in each number, and then we want to concatenate these bits. Yes, the right part of these bits to one format, 8-bit. For example, this one. So, and here we have our so format. It's from the right by to the left. So here from the left to the right. So, but these this is the number, the value in a 8-bit format, and this is in a original, it's in a normal format, yes, it's 177. So this is a 2-bit quantization. So we transform the real memory volume, which have to have 2-bit quantized weights. So, and we transform it and we can storage it. Yes, and of course we couldn't run the inference model, but we can unpack it. Yes, and to run the inference. So this is about 2-bit quantization. Of course, about 1-bit. So I don't know. I didn't remember. So then some about this article, but it is what the same. So of course, congratulations. So you you heard an entire course of quantization from Hugging Face and deep learning .ai. So that's all. That's really all. So we had some code near, but it's really simple about packing and unpacking. So that's all. So about our seminar. So I want to tell you about activation aware weight quantization. It's some information of the article. I want to. It's AWQ method. So and here we can. I'm sorry. So just here it is. Think yes. So that's all. So 1 minute. So um, So it's great to quantize all weights in our model. So and to use it and to store it is an optimal way. Well, but some scientists, as you can see, um, they want to run the inference of the model in really small devices, for example, like smartphones, with restricted resources, for example, mobile GPUs. Yes, and we want to have still have high accuracy. So in such way, what the problem we have? Of course, a huge size of large language model. For example, GPT-3, so it have 175 billion parameters. It's about 350 gigabytes, yes, in floating point 16, only 16, not 32, even 16. So in 32, we have just 700 gigabytes, yes. And of course, we couldn't deploy it in a smartphone or the mobile GPU. So and if we want to make some traditional quantize methods, for example, some just we have a like post-training quantization. Yes, we lost the precision. So if we want to use the quantization aware training, it's a QAT method. So we have to allot computational resources for it. And another method we don't have. So it's don't use the great solution. So for example, GPTQ, it's the popular quantized method, so it can overfit in a calibration data. So and we lost these our generalization of the large language model. So, and this is the solution. So these methods, AWQ. So it's the key point of these methods is so not all weights in a large language model equally matter. So because if we protect only 1% really vital weights, yes, we significantly reduce the loss. We significantly reduce the error of the computation, and the importance of these weights. So we can define not not the value, yes, not the value or number, yes, or but in a distribution activation. So if we have some channels with huge activations, which transform the main features. So, and this is the key point. This is the key point of this article. So it's what we want to detect activations with activation channels with a really huge values, and then we can say, so okay, so in this channel we have the vital weights, significant weights. So, and we want to protect these weights of the quantization. We store it. Yes. I will say about the protection of these weights. So we can just save these weights, yes, and quantize all another weights, and then we want to run the inference and have high accuracy. So accuracy. Great. So about the method of protection weights. So if so here's well, okay. So in quantization, so in just general quantization, we have mixed precision. So floating point 16 and int 4. But for these salient weights, which we defined by the activation channels, we use another scaling methods. So first of all, we so we just make the scaling of it, but not the in 14.16. Just we rely on the activation distribution, and then we transform from these distributions of the activation. If we have, for example, the more activation is, the more significant weights is, and the less scaling of these weights will be. That's all. So we have some formulas, yes, for example, for this one, yes, we have some scaling methods with weights, and here's the max of the weights, yes. So, and we just round it, and here the number of quantization bits. That's all. So, so the simple, yes, we rely on the activation distributions, and then we scaling based on this distribution the significant weights. That's all. So this method works really great. So they have tiny chat of the mapping AWQ onto AIH platforms. So, and this is the deploy combined with tiny chat. That's pretty simple. So, and as you can see, they some GPQ or RTN. So it's the popular quantization methods. Of course, they quantized lost a lot. So, and then really save the memory. AWK don't do so, but the accuracy of quantization, as you can see here, we have another. It's not the accuracy. It's just precisions of this. So okay, experiments, and yes. So this is visual language model. They contact. I'm sorry. Misclick. Here. Yes. So as you can see, key. So we have the more accuracy in the visual language model in all formats of from 0 shot to the 32 shot. So, and it's great. It's great, and as you can see, so it works really great. We have much more accuracy, some quantization results with the code lemma. So and this is the key. This is the method of AW key. So and of course it was a big improve, and this is how like we can inference large language model in smartphones. Yes, and that's all. So let's see some theory. We discussed some quantization. For example, post-training quantization, it's applied after the model has been trained. So, and it's sometimes it's it works great. So, so we in post-training quantization in this method, it converts a pre-trained floating point 32 model to a fixed point format without retraining. So, and first of all, we set the range. Yes, we determine the clipping thresholds of the quantization mean and quantization max for a quantization, and we these quantization methods include several points. Yes, so we use for min max. Yes, it converts the full dynamic range, but it is sensitive to the outlines. There is some optimization, so mean squared error and cross entropy. So here we have quantization aware training. It simulates quantization during training, allowing the model to adapt to quantization noise. So these methods include some straight throw estimator. So it's this estimator approximates gradients for a non-differentiable rounding operations. So, for example, just backpropagation, just for enabling backpropagation. So, batch normalization following, so it merges the batch norm layers into preceding linear layers for efficient inference. So it's great. It's great, really great method. So in QAT, so learnable quantization parameters. So they learn scale factors and 0 points during training. So in a linear quantization, you have some static linear these parameters. Yes, so 0 points and scale. But in these methods, it's they are learnable. So so QAT so achieves near 14.632 accuracy for 4-bit weights and activations in many models. So and it's really great. I really recommend you to read this article to see some additional information about them. So this is the linear was the linear quantization, and here the practice. So we will use symmetric quantizer. So for example, here we want to define some num bits. Yes, so 1 bit, in which bit we want to scale. We have our quantization min and quantization max during the formula is some values. So, and this is the quantization. We just use the maximum of the weights, yes, then we scale max to the max value to the Qmax. So we scale it. Then we normalized all weights with the scaling factor, yes, and then we round it, and then we clipping quantized weights just in a Qmin and Qmax. So that's all. And when we return quantization weights, dequantized, we don't want to not want to dequantize, but it's pretty simple. We can use something similar from this formula. So that's all. Well, so how it works? So we have our class. Want to display. So we have some batch size. This is our original weights, as you can see. So it's the floating point 32 type of the data of the weights. So, and this is the quantizer. Then we use our quantization methods and our quantization weights. So they begin. So this is the -2, -5, 48. That's all. So, etc. So, and as you can see, we saved some the distribution. So if you see here, yes, we have our weights from no, I don't know the minimum. I think here it is. Yeah, here it is, 0.14. So, and the maximum value is, I think, 0.11. Yeah, it is 0.11. As you can see, and the same in the same parts of the matrix, yes, and we store we saved our distribution. Here's the maximum value, and here's the maximum value too. 52. So, and this is the minimum value here, and we have the -68. That's all. And we reduce the memory compute. So we reduce the memory, and we have only 8-bit. So I think we can in the 4-bit. As you can see, we have the same, yes, but here we have no two maximum values. Yes, here the 3. It's because the 0.11 and 0.10 is really near in a distribution. So that's why we quantize just in this case. So, but overall, we really reduce the memory, and it's great method to just in baseline of the quantization. So, and dequantize, it's pretty simple. I'm sorry. So sometimes, of course, we have some errors, quantization errors, which store in scaling factors and 0 points. And of course, sometimes if we reduce a lot, we can quantize really extreme. We use extreme quantization, just in 8 times, as you can see. So from 32 bits to the 4 bits each. Oh, I'm sorry. What's happened? So sometimes we have some errors, and that's why we can lost the precision. But if you can see, as you can see, so here we have zeros. Yes, that's true. We have just 4 zeros. Other values, it's pretty similar to the original weights. Yes, it's a really small error, I think. So, and these values, so they was really small. So if we quantize just in 8 bits, yes, for example, here, we can dequantize it with a great precision. We have, of course, we have the less error. We have it, but it's the less. So this is what the linear quantization. I'm sorry, no. Please no. So, and here we have a double key activation of weight quantization. So, and here the key idea, okay, we discuss it. So, and here the method, the class of the AWQ symmetric quantizer. So this is the similar, but we use our average activation. We mean all our activations, yes, with scaled weights based on this distribution of activation, and then we use the same. So the same formula is as we did here. So that's all. Then we return quantized weights. We don't want to use the dequantize because it's so pretty pretty hard. So, and here it is. We had our some activations, so some random activations, and we had our weights. Yes, this was so it's the same weights, original weights here. So, and we can compare as, so we have the same distributions. So as you can see, we don't have some we don't have some extreme values in a int, because we use int 8. If we want to use int 4, it will be the same, just pretty similar for the linear quantization. Yes, but we still save the distribution of the weights in a matrix. So as you can see, here was the maximum value, here was the minimum value. So that's all. So this about AWK. So, and if you want to experimenting, so about evaluating, so we can do it, but it's because I don't have the GPUs. It's sometimes it's really hard to make these experiments. I have an access to all Llama repositories, so even in Llama 4, I choose the Llama 3.2 on the 1 billion parameters, and I download it. So, but what's the problem? It works. So we have a generation text. Of course, it's the dummy text, so it's just in a text loop. Yes, so repeat the same phrase. So it's the input phrase. So, but of course, I can launch the quantization parameter of the real quantization model, but it's really long. So because and I just crashed my notebook. So because I use only CPU, and for such quantization operations and computation, we have CUDA kernels. So, and I don't have them. I don't have them in these laptop. So and I use these model in a server. So sometimes it's not. I couldn't show you this notebook because notebook in a server. So I use only in the scripts. So in a conclusion, so I want to tell you, so the neural network quantization, even especially large language model quantization, is essential for deploying some efficient models on edge devices. So PTQ quantization, so it offers a lightweight solution for a moderate quantization, and QAT enables aggressive low bit quantization. Some AWK allows us to quantize the model for our mobile or small devices with a small computation memory or small computation resources. So I think future work in this area, so and the current work, of course, may focus on heterogeneous, some bit weights and broader hardware support, just in a Yandex, for example, in the Yandex lab, something else. So I think that's all for today. Thank you so much for hearing this part of our seminar. So if you have some questions, I think you can ask me now. Some links. Yes, for articles you should. Some links. Yes, of course. So no problem. Okay. Well, if you have no question, or you can even if you will have some in the future, you can write me in the chat. So I think that's all for today. Have a nice day. So goodbye.
Thanks for the.
Yeah, goodbye.
Thank you. Have a nice day.